So thank you very much for coming to this talk. I'm super excited to be here today and to speak with a lot of people that really work into this space. Today's talk is going to be about bring your own vulnerable driver attacks on Secure Boot. I am Fabio Pagani. I work as a vulnerability research lead at Binarly. And let me just jump straight in the agenda because it's pretty packed. So I will start with an introduction about bring your own vulnerable driver attacks, and in particular about their implication for the UEFI ecosystem. Then I will present a taxonomy of attacks against Secure Boot. I will tell you how we found dozens of Secure Boot bypasses, and also about some recent efforts in hardening the UEFI shell. Finally, I will also give you a little peek into a new research that we still have to publish, it's still ongoing, and it's about mitigation in the UEFI ecosystem. How many of you have ever heard about BYOVD, Bring Your Own Vulnerable Drivers? Okay, thank you guys. No worries. So this is a security problem, or better, it's a security technique where attackers take advantage of vulnerabilities in legitimate Windows kernel drivers, which are signed and trusted by the operating system, right? So the attacker simply finds a driver which is signed by Microsoft or by any of the certificate that the Windows kernel trusts, and this driver has the vulnerability. At this point, the attacker can simply install this driver into the victim machine, and then after it installs it, it exploits the vulnerability at kernel level. So it's really able to go from user space to kernel space and to elevate privileges. This has been a technique that's been around for a long time. It was mainly used by APTs in the past, but nowadays this is also found in commodity threats such as ransomware. If you want to know more about this, there is this blog from Talos Intelligence, which is extremely good and extremely recent too. Okay, so but why are we talking about the Windows kernel when this is a UEFI specific conference, right? Well, it turns out that UEFI has a similar signature verification system, and that's called Secure Boot, right? At the end of the Dixie phase, the BDS phase starts, and the UEFI boot manager, when Secure Boot is enabled, will verify if the bootloader is trusted and verified. This determination is based on the content of two NVRAM variables, DB and DBX. DB contains everything which is trusted and allowed. DBX contains instead what's revoked and what is not trusted. So one of the key questions that our research aims to answer is, what is the impact of this technique in the UEFI ecosystem? And this is super, super important because if we find a driver that can be abused as a bring your vulnerable driver attack, then we are going to be able to break the chain of trust, which is rooted usually in the platform from bootguard, and that should go until the operating system. If you're able to execute code before the operating system starts, then it's game over, and I will show you a demo about this later in the presentation. So before actually started this research, we took a look at Secure Boot and in general at the verification system, and we came up with this taxonomy of attacks. We will cover two of them today. The first category contains what we called double-use modules. These are trusted programs which expose a functionality that can be misused to run untrusted code. A nice example of this is the UEFI shell, and I will tell you a little bit later how it can be misused to run untrusted code. Second one is instead the most common BYOVD attack. It's programs, it's modules which are trusted, which are signed, but which are exploitable. So, as I told you before, we really want to understand how large is the attack surface, right? Do these drivers exist or not in the wild? So, this is the high-level plan that we came up to try to answer this question. We start to by building and collecting a comprehensive dataset of UEFI modules. Then, from this dataset, we determine which of these modules are trusted by real-world firmware. And finally, we take this subset of trusted modules and we scan them. We try to understand if they are double use or trusted but vulnerable modules. So this is how we build this large dataset of UEFI modules. We use three main sources. First one is an internal collection that we keep of UEFI firmware, which is gathered over the past 5 years, contains thousands and thousands of firmware images. We use private telemetry data that comes, for example, from the APK.fail detector. And also, we downloaded the UEFI modules and UEFI firmware from public threat intelligence feeds, such as VirusTotal. All these resources combined resulted in over 10 million module indexed inside database. So now we take this database and we check which of these modules would pass the secure boot verification on recent firmware. And this is simply done by extracting the DB and the DBX from a firmware image and then matching them with a secure boot algorithm and see which of the 10 million are actually trusted, right? What we discovered is more than 7,000 unique modules which are trusted by recent firmware and which will pass secure boot verification on some of the recent hardware and recent devices. Now, this might seem a small number in comparison to the 10 million that we have in the database, but keep in mind that a vulnerability in any of these trusted modules can be used to bypass secure boot on the device, and so can be used to break the chain of trust. So with these 10,000 modules, we then try to scan them. We want to see if we are able to find vulnerabilities in there. To do so, we use our own technology, which is able to uncover basically 0 days in these modules, which are often, as you might know, related to handling of environment variable, but also we cover other bug classes. And by scanning these 7,000 modules, we were able to find one vulnerability that got also a CV assigned. And this is interesting because the vulnerability was found in a module signed with the Microsoft third-party UEFI certificate, which is extremely commonly trusted by devices out there. After we reported this to Microsoft, it actually turned out that there was not a single module that had this vulnerability, but there were 13 other versions of this module with this vulnerability. So Microsoft had to add, in total, 14 entries to the DBX during their June Patch Tuesday update. Here you can actually see the vulnerability. It's actually very simple. The problem here is that this module was reading a variable, an environment variable, and storing its content in the var content. And then a few lines later was trusting this content, this address, and was using it for multiple memory writes. So as an attacker, I can basically simply specify any address into this environment variable, and when the module will run during the boot process, the module will write these constants to my own address, right? So this seems also a sort of constrained capability or a sort of a constrained writes to memory, but I will show you in a second that writing even a 0 to a attacker-specified address is enough to bypass secure boot. So this needs to be taken extremely seriously. In terms of double-use modules, instead, we focused on the UEFI shell. This is because the UEFI shell has been found in the past in a few isolated incidents that was the UEFI shell was signed with some of the keys trusted by firmware, right? And we chose also this target because the UEFI shell has a very large attack surface. It has dangerous commands, such as the command, which, as you can see, can be used to modify memory at will. And also, it reads command from the startup.nsh script. So it's the perfect candidate for executing arbitrary command during the boot process, even when secure boot is enabled. What we found is that signed UEFI shell are not an isolated incident. They are an ecosystem-wide issue. We found more than 30 UEFI shell which are trusted by hundreds of devices and which can be used to bypass secure boot on these devices. There is a disclosure ongoing, so I cannot give you more details about this, but follow us if you want to know more in the future. So now I want to sort of give a glimpse on how we can convert a write to memory to an untrusted code execution. So how do we exploit this command to arbitrary write, arbitrary execute command, arbitrary execute code, sorry. The core idea is very simple. We simply use the command to overwrite with 0 the gsecurity2 variable. This is a global variable which holds a pointer to what basically implement secure boot. And as you can see in this snippet, which is taken from the load image function exported in one of the UEFI tables, when gsecurity2 is null, the file authentication is not going to be executed, right? So by simply writing a 0 at gsecurity2, the secure boot will basically be disabled because we won't call the file authentication on any module that we try to load. And with this core idea, we developed a proof of concept, which looks roughly like this. From a privileged operating system shell, we copy the signed UEFI shell and the startup.nsh script on the ESP. Then we place a second module, which is what we call the malicious payload, on the same partition. And finally, we configure the boot manager to run first the UEFI shell and then the unsigned module. Okay, so the environment is ready. Now we reboot the device. And what happens is that the boot manager executes the UEFI shell because we just instructed it to do so, right? The UEFI shell will automatically execute the startup.nsh script, which contain the command which overrides gsecurity2 variable. I know it's a little bit of a long chain, but trust me, it works. At this point, secure boot is disabled. gsecurity2 is 0, and so we can simply load any unsigned module with any malicious payload and execute it successfully. So here I want to show you a video of how the attack looks like. As you will see in a second, okay, there it is. So here we are dealing with an up-to-date Windows 11 machine with secure boot enabled, so everything is there. Now we prepare the environment for the secure boot bypass. So we copy all the files to the ESP, we set up the UEFI boot manager, and finally we reboot the device. Okay, don't forget that secure boot is enabled, right? So we should not be able to run untrusted code during boot. But in a second, you will actually see that our malicious payload was executed, and we are able to print some ASCII art, and this happens from the UEFI world, right? And once again, let me stress it, this should not be possible when secure boot is enabled. Now, the chain of trust is broken, and we can basically do a lot of nice things. And our demo does not stop with some ASCII art, but we also load a bootkit. We decided to load to test the Red Lotus bootkit, which is a bootkit written entirely in Rust and which draws inspiration from Black Lotus. And you will see here in a second that we attached the debugger to the machine just to see some output from the bootkit, and which is going to be shown on the right side of the screen. But in a second, you will see that the bootkit is running. it was able to hook inside the Windows kernel loader, and then it was able to jump straight into the Windows kernel, and is now searching function and hooking them and patching them. And these prints, I know that are a little bit small, but this is the bootkit which is already doing its nasty stuff. In a second, you will see what these nasty stuff are, because the capability that this bootkit gives is that an untrusted process can run an unsigned driver from user space. So you will see this client, which comes again with the bootkit, and you see that we specify a driver.sys file. I know it's a little bit small, but this driver.sys is completely unsigned, but since the bootkit patched the kernel, the driver can be installed. And you will see in a second, again, that our driver is actually printing some stuff. And this means that we have kernel-level execution, which started from an untrusted, from an unprivileged user space program. So again, it's pretty bad. All right, so how do we solve this problem? I just want to tell you a couple of things that happen around the UEFI shell. One of these, this is a commit that happened in 2024 from Jared Hoffman from Red Hat, which basically added a patch to the shell build system build file, so that the shell is not built when secure boot is enabled. All right, this was a good first step in the right direction. Other thing that happened, this happened actually after we published some of our research, is that it turns out that some folks at AWS knew about this problem, right? And they had an internal patch for their own version of the shell that basically aborts execution when the secure boot is enabled. And this is, of course, a way to harden the shell even more, because even if the shell is going to be signed by mistake, then the shell will not execute when secure boot is enabled, right? Okay, so now let me just take a little bit of a sharp turn, because I want to give you also some results about this other mitigation research, which is upcoming. We spent quite a lot of time looking at the mitigation in the UEFI ecosystem, in the reference implementation. And if you follow a little bit the security of UEFI and what happened in the past few years, you probably heard about logofail, bootkitty, pixie fail, which is actually some bugs that were found by Quark's lab in the IPv6 networking protocol of this networking stack of EDK2. And most of these findings do actually come with a proof of concept. So this means that they come with an exploit for that bug. And what makes these exploits and this vulnerability easy to be written and to be exploited, right? Problem is that the UEFI firmware, unfortunately, lacks basic mitigations. I will just cover real quick a couple of things that we found about stack canaries, which, as you might know, are one of the probably oldest and easiest mitigation to be implemented. We place a canary between the return value and any buffer to make sure that if the buffer overflows, then we have a way to detect it. And actually, good news here is that recently there's been some work in the reference implementation and the support for dynamic stack canaries landed and was integrated in the reference implementation quite recently. So I think this also connects to what Mark was saying during his keynote, that there is actually some push for security features in the reference implementation. And this is honestly great work. It's great engineering security. And this solution can be easily integrated into UEFI application and UEFI drivers. Before this contribution, though, the support was very small. Stack canaries were only enabled for ARM targets, and for the rest of the targets, they were explicitly disabled. The other mitigation that we took a look is no execute NX, which basically means that when we map a UEFI driver in memory, we don't want to have the code section to be writable, and at the same time, we don't want to have the data section to be executable, because this makes the life of attacker much, much easier. Reference implementation has different knobs and with the PCDs to customize this mitigation. The PCD image protection policy decides which modules are protected with read-only code and non-executable data. The NX memory protection policy decides instead which UEFI memory types are marked as non-executable. And then we have a PCD also to decide if the stack shouldn't be marked or not. So there is great support. Once again, the defaults were not were suboptimal in a sense that for x86 we were protecting, well, the reference implementation was protecting only images loaded from firmware volumes, and it was disabled for all the other sources. And for ARM images, instead, it was actually much better since the policy was covering all sources, and also all the non-code regions, including the stack, was not marked as executable. So that was good. These defaults actually show up, and you can actually see them when you check for modules and firmware in the wild. In terms of stack canaries, we found that only a very small percentages of the analyzed Dixie drivers use stack canaries, and any of them was for x86. So all of them were basically for ARM devices. In terms of no execute, the situation is a little bit better, but again, only the 10% of the analyzed firmware enforce a correct memory protection policy, and in most cases, the bootloaders remain unprotected. Another thing that we, and this is the last thing that I want to share about the mitigation research, is that mitigation sometimes they are difficult to understand, and that must be applied carefully. For example, there, if you go and look at the reference implementation where the NX is actually implemented, you will see this if condition. And what this if condition basically implement is that the section alignment specified in the PE header must match the EFI page size. If this is any other value, NX is not going to be applied, even if the PCDs were correctly set. And this is a problem, right? And it shows basically a critical gap in practice. We found that 70% of Dixie module didn't have this specific section alignment in their P header, and so they were not going to be protected despite all the PCDs were correctly done. So as a conclusion, as operating systems and application layer security have actually hardened, attackers and actors are actually shifting to firmware level attacks, and yes, to try to get a chance to run at this level, because it's very, very powerful. We've seen in the past more and more threat actors interested into this, and just recently, researchers from Asset were able to find their first ransomware completely implemented with UEFI code. And not only that, the ransomware was also coming with a bypass for secure boot. So that's pretty scary. Secure boot represents the last line of defense against this type of threats. So we really need to put effort into hardening it as much as possible. And again, it's very nice to see that things are happening in the reference implementation when it comes to mitigations, but they are largely absent in the ecosystem. So we know that the reference implementation is not what is running on our devices. And once code is committed there, it needs to be also implemented and taken and integrated into the UEFI solutions that actually, in the end up on our devices. So I think that was it. Thank you very much for coming to the talk. And if you have questions, we have, I think, 5 minutes now, but I'm also going to be around for the days.
Thank you for excellent presentation. It's very interesting. So, is there any website that we can visit to find out all the known issues in the UEFI, security issues?
Yeah, I mean, you can definitely follow us. You can definitely follow our blog. We publish a lot about UEFI research and the vulnerability that we find. We usually have a blog post. We have advisories also on our website too.
Thank you.
Yeah.
Hi. It sounded like the majority of the cases you identified were signed with non-globally trusted keys. They were vendor-signed objects rather than Microsoft-signed objects. For those systems, would the attack you demonstrated have changed the PCR7 measurement, or was the vendor key always being measured during the boot because of random other stuff happening?
Yeah, thank you for the nice question. So it is true that the shells were always signed with the vendor certificate, but the module that we actually found with the arbitrary write that was signed with the Microsoft third-party certificate. So in terms of measured boot, I should double check that, but I don't actually think it's going to be stopped by. Or actually, no. I think I'm wrong. I mean, let me just double check that. But I think the bootloader is measured, right? So that will probably change the state of the TPM, right? And so that will be stopped by measured boot.
Thanks.
You showed us quite a few bits to this where a lot of vulnerabilities or misconfigurations seem quite actionable. For example, 68% of the Dixie drivers don't have the correct alignment for NX protection. Do you have any plans to follow up on this, either by opening patches into the upstream or by designing some kind of a more global system where all of Dixie drivers will have to have correct alignment? Is there any plan to follow up on these things?
Yeah, that's not something that I know honestly how to answer. In general, when we find vulnerabilities and we find problems, we are always happy to work with vendors. I mean, if it comes to open a couple of patches, for example, to a couple of PRs to solve this problem, that's perfectly fine. But in other cases, it requires really a lot of commitment, a lot of security engineers that actually work on the problem. Stack analysis seem like a very basic mitigation, but you should go and check the amount of work that was needed to actually implement it. So I think that's, I mean, I'm not sure if that's on us or not, right? Because we are a security vendor, we do software supply chain, we are not a firmware vendor, right? I understand that there is a lot of work, but I mean, I really hope that with our research, we are sort of able to move a little bit and to raise the bar a little bit higher. Yeah, exactly. I think that's the point. That's the plan. We submitted. We opened we got in touch with CertCC, which often help us when it comes to this type of ecosystem-wide vulnerabilities. But that's exactly what's going to happen, I guess. The vendors will need to add the Authentico dash of this shell to the DBX.
So regarding your observation about the percentage of modules that have the proper alignment, the addition of NX support into UEFI is air quotes relatively recent, end quote, happened a couple of years back. And then as part of that, the discovery was made that, okay, in order to make this happen, we need to have this alignment. And that's why you've seen code go in. Have you looked at this giant collection you have of, however many million examples of drivers? Have you looked at the time those drivers were released and charted it over time?
Yeah.
Showing the progress. I mean, any sample at a point in time is going to look kind of low until you get much, much further down. But if you looked at that, and do you have that data and the curve of how things are progressing?
I don't have it, but we could probably have it. I mean, because we usually have the images that we have also a timestamp when they were sort of built. So that's definitely something that, and it's actually a very interesting observation. I must say, though, that we selected only recent firmwares, so recent images. We don't go and select. Exactly. That's just a subset of recent, like the last version of the firmware for the specific device type of thing. But I agree with you. I mean, if NX was not even there, then I mean it's a little bit unfair. That's something that's actually very interesting to measure. Yeah. Thanks.
All right. Thank you, Fabio.
Thank you.